First we follow the edge backwards, all the edges backwards. And then we are going to do, in the next step, a backward slice of all the instructions that were reached from the previous step. So now we don't have anywhere else to go backwards from enter, so we can stop, and this is a code slice on a backward code slice of add AXBX from this example. And these are the, the bolded would be the actual slice itself. A forward slice is done exactly the same way, except you follow the edges forward instead of backwards. There's not a whole lot left to say about that. You just, go here, and then that gets you here, and you follow all this stuff around. This is your forward slice of the current example, and this is the part that's bolded would be what you get. So, problems with code slicing, and there's lots of them, as I've already talked about. But any error in analysis could quite possibly lead to a completely incorrect code slice, right? Because say you're missing an edge that goes to somewhere important that has like 15 edges in it or something, then you aren't going to get any of that information, and that's pretty much useless at that point. So, and the amount of space needed to store is very great. The following metrics are from my colleague's code. I mean, they were breaking the 2 GB limit on a 1 meg sized binary, trying to analyze it, and now it's down to 584 megs because the guy who was working on it is really stellar, and he knows how to do a lot of optimization. Used to take 20 minutes to do the analysis. Now it only takes about a minute. So it's possible, but it's quite a journey to get there. How can we use this? This is the researchy portion, right? It can actually be used to assist in signature analysis, even though we talked about that at first, because that was for the detection. It doesn't need code slicing after it. You could do the code slice before. So the problem that I was talking about with the no-op instructions, types of instruction sets, that can be alleviated here. We just run a code slice on the signature and find I'm getting ahead of myself. Find possible signatures in the binary, starting and ending instructions, and then run your code slicer through there. And if you find anything that doesn't do anything, as in, if you do a code slice on it and it doesn't get anywhere outside of it, or it doesn't actually affect anything, then you can just strip that out as do nothing code and call it a no-op, right? And then that can be, you can pull that code out, then run your signature analyzer on it again with the actual signature analysis, and that will find that code because everything has been stripped out of it that doesn't do anything. So, the best and most desirable security is to have a resilient program from release, right? We don't, a lot of people want this. It's always going to be talked about. Just an important thing to think about. Code slicing can help. Run code slicing on a signature itself, not on the binary, but on the signature. Create possible out edges in the appropriate places, like if something is defined. For flow dependence, possible out edges could tell you which registers used in a certain way might be affected by a known security threat. Control dependence, the same thing, might be skipping licensing code or something like that. So, note, analyzing flow dependence and control dependence in the given way requires to not just know the algorithm for code slicing, but to truly understand what it represents. That also understands, in addition, you need an understanding of what the malicious code is intending to do. So this takes a lot of hand-holding, but the analysis is there. So it gives some additional insight into the behavior of the malicious code represented by the signature. The behavior can be caught, by a separate thread or process, and which can alert the user or deal with or isolate whatever the problem is that you're running across. This is essentially what virus scanners do, right? But we're not talking about that specifically. They don't use code slicing, I know that for sure, and they don't. Their analysis is a bit different. So I went through that kind of quickly. I didn't. But is there any questions that anybody can answer? Any possible? Sure.
How do you handle packets?
Turn your mic up.
How do you handle like packet binaries?
Packet binaries?
Yeah, you write a packer that would pack the source code, and at runtime it would unpack the source code.
Like kind of managed code kind of stuff? Is that right? Or what?
No, like every guy that writes viruses writes a packer for their virus. So it's a little stub that takes the binary, the code, it packs it into something that would trigger a different signature, and at runtime it unpacks that code and jumps there.
Oh, run. Okay, so you're talking about run. Well, that would be the idea of the runtime checker, like right, the running a separate thread or process, right, that does your signature analysis while the process is running. So
but are you gonna check at all times that the process is running?
Just whenever the context is switched to that particular process or thread. Right?
Every time.
Yeah.
Every context switch, you're gonna do a check.
Anytime that the process is running. Yeah. I mean, this is just researchy stuff, right? This hasn't actually. I don't have any proof of concepts or anything.
But what I'm saying is like all these things, all these signatures, like they've been trying to do it like 15 years and they haven't been able to come up with something that works actually. Like I don't know if you saw that in DEF CON there was a contest that if you could beat 13 antivirus companies, and it took 13 minutes for someone to beat them all.
Wow.
So.
Sorry. Sorry.
Thank you.